Hi, good day. Welcome to this brief summary of the research paper Development of an Electrical Power Takeoff System for a Sea Test Scaled Offshore Wave Energy Device. This video gives a brief analysis of the subtopics outlined by the research paper, which gives an appreciation for the work done by previous researchers so that any individual can have a basic understanding of the issues and achievements obtained thus far from the development stage of the device. Moving into the objectives completed by the research, let us outline the operation principles of the wave energy device. What is a wave energy converter? This is a device that captures kinetic energy from the imbalances caused by the collision of wave motion onto a mechanical device or structure. There are many means of harnessing energy from the waves, but the principle used in this design is the oscillating water column. Learn how it works. This illustration below gives a visual representation of the processes at hand. An incoming wave crest creates a rising water column which forces air out of the system, in turn spinning a turbine which turns mechanical parts in a generator to create energy. During the falling of the water column, the opposite action occurs and alike creates energy. The similar action occurs in the bent backward duck boy wave energy converter, which is the device studied at hand. The power takeoff system is the main component of this device. This senses sea conditions. A motor then spins the turbine to a minimum required torque for operation. This converts pneumatic energy into electrical energy. This dissipates the generated energy as electrical energy in the system circuit. An integrated controller monitors and logs all data pertaining to the device operation. This integrated controller is then remotely used to control the device via telecommunication links as the device is in remote location. Following the main features of the power takeoff system, its main components are the Wells turbine and duct. The Wells turbine is particularly responsible for generating the rotation of the shaft in one direction regardless of the direction of the wind. This explains why the system provides a positive drive regardless of wind direction. 2. An electric machine, which is a brush motor. It is advantageous in that it has a permanent magnet which creates a permanent field flux which works under all conditions. It also acts as a fail-safe brake for deceleration. The machine is also simple, which is only required for turning a turbine. Its only disadvantage is that its parts are hard to source and it works under low voltage conditions which limit the device design. A generator to recharge the system battery, a DC to DC converter which converts voltage from one form to another, a programmer logic controller, electric load bank, and an electric power source which consists of 7 12-volt batteries connected in series. The power incoming wave governed by the pole electronic is open to deactivate the brakes on the turbine following X1 closing. SW1, an insulated gate bipolar transistor, quickly switches the state of the system which passes current through the diode D1 and charges the capacitor C1. This allows the motor to generate torque in the turbine. As the system captures energy, X1 is open and X2 is closed. The SW2 allows a fast switch in the system and the gate driver regulates a high current input to the system. The charge capacitor buffers the circuit from damage as the power is stored. For the incoming speed omega star, the speed proportional integrator controls the motor speed through controlling the clamp which regulates the current in the system. The current proportional integrator controls the gain of the system voltage based on the response. This is looped to obtain a feedback through feedback for adjustments. The machine constant then determines the machine torque, which is disturbed by the turbine torque. With the torque compared to the moment of inertia and friction of the system, the output speed is obtained. This is looped until the desired speed is obtained for power generation. For the controller to manipulate the system, input is required. Input is done through instrumentation. This covers the areas as follows. One major issue with this design, however, is the speed optical sensor, which responds to no significant input. It generates short pulses indicating high speeds, and it also generates output due to sea splashes or sprays. Overall, both electrically and mechanically, issues that shape the design philosophies are as follows. Limited access to troubleshooting and potential loss of data due to weather limitations, which limits gathering of data from sites. High cost of downtime of the experiment. With these considerations, the following factors were improved upon to reduce any problem. Moving from the explanation of the device to the testing, development, operation of the device, this is the result obtained for the power output and wave conditions for a test done in week 3 January 2009. From the results table, it can be seen for power versus time, the capacitors, diodes, and insulated gate bipolar transistors play a huge role in ensuring that the electrical circuit is not overloaded due to peak rises as seen. The graph below, wave height and period versus time, gives a direct correlation. A high period and wave height and long period gives a high power peak and mean values as seen, and a low height gives the opposite as seen at 135 hours and 50 hours respectively. Between 24 and 48 hours, errors in the sensor might have given false readings. These graphs give the behavior of the system in heavy sea and moderate sea conditions respectively. Power is not supplied to the system to compensate for friction and windage losses in the system. Power is not drawn from the battery bank to maintain the speed. This creates dips in the plot as shown. This scatter graph shows the electrical power output variation with turbine rotational speed. This was obtained from a study done in October 2008 to April 2009. The graph may be interpreted as having higher gains in energy in comparison to losses in activating the turbine for operation. This is true for most operation speed as indicated by the key. Some variations are shown at the base, which may be as a result of error from the optical sensors and downtime of equipment, right here. From these results, the system has performed sufficiently to move from the development stage for further testing. From the overall report, it is seen that the bent backward duck buoy wave energy converter is feasible enough to be further tested for future use. Thank you for listening on this report.